A short revision video for CE141, Mathematics for Computing. The first thing to look at is if you go to the Module Resources section on the course Moodle page, you'll find these items here. So first of all, there's a PDF at the top here, which will give you some information on the format of the examination and some tips for revision. We've got two revision classes in this subject. And rather than me trying to cover the whole syllabus in those, which obviously will not be practical, it would help me if you could give me some guidance of what you would like help in. So I've set up 4 poll questions here, 2 to give you a first choice and a second choice of subject matter you'd like me to cover, and the second to give me first and second choices over particular past exam questions you'd like me to look at. And then finally, at the bottom of this section, in common with all other modules, we've set up a frequently asked questions section where you can have a look to see if any question you may have has already been asked and answered. If not, you can add your question. And then other students are quite at liberty to answer questions if they want to. And of course, I will look at this every so often and try and answer all the questions as best I can. Okay, so to briefly outline the module, I've got a short presentation. Of course, we had 5 subjects: propositional logic, combinatorics and counting, set theory, probability, and matrices. So first of all, in propositional logic, we were looking at the idea of a proposition, which is just something which is either true or false. As with algebra, numerical algebra, it's useful to have use symbols for unknown variables with unknown values, and I was using small lowercase p, q, r and so forth propositions. And then we can combine them with a set of logical operators, and which is given by this wedge symbol, or which is given by the v symbol, or not with this other symbol here. And then obviously we can construct compound propositions from component propositions. So for example, P and Q is itself another proposition which can only take the values true or false. But of course its values depend on the values taken by P and Q. There is then of course a syntax for compound propositions. And in this, not takes precedence. So in this expression here, P and Q or not R is done before the result is ORed with the term in brackets on the left-hand side. After not, the next thing to be evaluated is brackets, and there is no precedence as in ordinary algebra. In ordinary numerical algebra, multiplication has precedence over addition, but in propositional logic, and or have the same precedence. And so if you have something like P and Q or R, then you need to put brackets in to say which of those will be evaluated first. And then the 2 main techniques we looked at in this were truth tables for compound propositions. And these are just exhaustive tables of the values that the compound proposition take for every conceivable combination of values of the component propositions making it up. Of course, it's nice to do this in a systematic way. And the standard thing is to start with columns for each of the component propositions and to go through all possible combinations of component propositions. Well, it's quite helpful to do this in a systematic way by using something like a binary count. So for example, if there are 3 component propositions, P, Q, and R, then the values can be taken in the order false, 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 true, false, true, false, false, true, true, and so on, like a binary count. Or you could start from true, 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 and then go to true, true, false, true, and so on. But if you do it in a systematic way, you'll avoid repetitions and you'll make sure that you don't miss any combination out. Of course, any proposition can be fully analysed by the truth table, but obviously if it contains a large number of component propositions, the tables become very long. So the second thing we looked at were logical identities. And the idea of a logical identity is that you have 2 compound propositions separated by the equivalent symbol, this three equal bar symbol. And what that means is that the two propositions either side of that symbol always take the same value. They're either both true or both false for every combination of the values taken by the component propositions making them up. And of course, one of the classic examples is one of De Morgan's identities, which says that not P or Q is identically equal to not P and not Q. So it doesn't matter what values P and Q take, those two sides will always evaluate to the same thing. Of course, you can always, in principle, prove that an identity is true by drawing up a truth table for both sides and making sure that they always evaluate to the same value, either true or false. But if you have, say, 5 component propositions, then the truth table will consist of 2 to the power of 5, that is 32 rows, and that's rather tedious to write down. If you've got 10 component propositions, it becomes impossible with 1024 rows to the table. So it's useful to also be able to prove things by algebraic manipulation. So starting with some simple identities, manipulate both sides according to some rules of algebra, and construct more complex identities. And the sort of thing you can do, of course, is do the same operation on both sides of an identity, and you'll preserve the equality of both sides. Or you can substitute any sub-proposition on one or both sides of the identity with something which is equivalent to that proposition that you're replacing. And the idea is to start for some very basic and in some ways very obvious propositions, which I labelled A1 to A11 or A1 to A13 in the problem sheets. In the exam, you will have a set of basic propositions A1 to A11, exactly as in previous years, which you can use as starting points for proving more complex identities. And then we finished off propositional logic by looking at 2 other compound propositions, the conditional operator, which is given by this right pointing arrow with 2 legs to it, and the biconditional operator, which is a double arrowed version of those. And then finally, we looked at tautologies and contradictions. A tautology is any compound proposition which always works out to be true, no matter what values are taken by the component propositions. And a contradiction is something which always works out to be false, no matter what values the component propositions take. So moving on to the second subject, that was combinatorics and counting. Really, the whole of this subject comes down to one idea, the fundamental principle of counting. And that says if you're looking to find out the number of different ways that some selection process can be carried out, if that process can be broken down into a sequence of steps, then the number of different possible selections of the overall sequence is simply the product of the number of options in the individual steps. And because of this, things like factorials arise in the subject. Of course, factorial n is just defined as the product of all whole numbers, integers, up to and including n. And you can write it down as a forward product or as a reverse product, obviously. So if you've got some selection process which has a number of steps, can be broken down into a number of steps according to the fundamental principle, then factorials arise when the options in each step get less and less as you proceed along the steps. So, for example, if you're working out how many orders you can arrange n distinct objects in, then the first object can be chosen in n different ways. That's the first step. The second object can now only be chosen in n-1 ways, because there are only n-1 remaining objects. That's the second step. The third step can only be done in n-2 ways, and so on. And this is why factorials arise in the subject. They don't arise in every aspect of the subject, of course, because you don't always have decreasing options in the steps. But one place they do occur is in so-called permutations and combinations. So we looked at permutations first. So what we have here is n distinct objects, and we want to choose k of them, and we want to find out how many different k object selections there exist where the order in which we choose the k objects matters. So choosing a red ball before a blue ball is different from choosing a blue ball and then the red ball. And the formula you get from the fundamental principle of counting in this case is that it's just the total number of distinct objects n factorialized divided by the factorial of n minus k. We also looked at permutations with repetitions, and the examples I looked at in the problem sheets were those in which you were looking at permutations of the letters of words where some of the letters were repeated. And obviously, if you select the same letter in different parts of a putative word to check in the dictionary, and the two letters are the same, they count as the same selection. There's no point in counting them twice. So the general result says that if your n objects are composed of I likeness sets, the first likeness set having k1 objects in it, the second likeness set having k2 objects in it, and so on, so that k1 plus k2 plus k3 all the way through to ki must equal n, then the number of different selections is n factorial divided by the factorials of the number of the cardinalities of the likeness sets. We then went on to look at combinations. So this is the same as permutations, except now we regard two selections which have the same objects but just chosen in a different order as being the same selection. So now we're not interested in the order in which things are selected, and that means that there are fewer options than we would have with permutations. In particular, there are fewer by a factor of the number of ways that the selected objects could be chosen, the number of orders in which they could be chosen. So there is this extra term in the denominator k factorial, which appears with combinations. So read this n over k in a bracket as being n choose k, and the formula is n factorial over the factorial of n minus k by the factorial of k. Of course, if we choose k objects out of a set of n objects, then we're leaving n minus k objects unselected. And so what we've actually done is just partition the n objects into two sets, one containing k objects and the other containing n minus k objects. And in some ways, that's a nicer way of thinking about the problem because it's symmetric. It shows there wasn't anything special in choosing the k rather than the n minus k, and the formula reveals that k and n minus k play the same roles in the formula. We then went on to look at the idea of partitioning when the objects are to be divided into more than two sets. So if we have n objects and we have little I sets that we're going to divide them into, the first we want to contain k1 objects, the second k2 objects, and so forth, all the way through to ki objects, then the formula actually turns out to be very similar to the permutations formula. We just take the factorial of the total number of objects and divide by the factorials of the sizes of the sets we're trying to divide them into. We then finished off by looking at choosing with replacement. So this, rather than choosing from a set of objects and not being able to choose the object that you chose in a second choice, you now replace it and choose again. So for example, if you're trying to look at the total number of three letter combinations from the English alphabet, there are 26 letters. And in the first choice, you've got 26 possibilities. In the second choice, you've got 26 possibilities because the second choice is allowed to be the same as the first. And in the third choice, you have 26 possibilities. So now that's a three-step process in which you're choosing 26 objects, choosing from 26 objects in each step. So the total number of choices, according to the fundamental principle, is 26 times 26 times 26. More generally, if you've got n distinct objects and you're trying to make k choices from that set of objects with replacement, then you just multiply the number of choices in each step, n, by n over the number of choices to get n to the power of k. Moving on then to the third subject, that was sets. And this is relatively easy subject. It's just there's quite a lot of notation in there. So the first thing we looked at was the idea of a set written out as an explicit list of members. So if you do it this way, use these curly brackets, curly left brace, curly right brace, and just list the members of the set between the braces. So, for example, the set A comprising the letters A, B, C, D, and the set N comprising whole numbers between 1 and 100. A set is the simplest data structure there is. There is no notion of order in a set. So even though I've written the members of set A, capital A down here as being A, B, C, D, I could write them in any order, B, C, D, A, B, A, C, D, and so on. That would still be exactly the same set. There is also no notion of multiple membership of the set. A can't belong to the set, little a can't belong to the set, big A twice. It's either a member or it's not a member. And then sets can be put together with a whole set of syntax in much the same way as propositional logic. So we have this funny curly E symbol to show membership. So if I wrote down the number 1 followed by this symbol followed by n, that would just be saying that the number 1 belongs to the set n. Anything with a bar through it like this just negates the meaning of the symbol without the bar. So that would mean not a member. And then the primary operations are union, intersection, and complementation. Obviously, the union of two sets is just the set comprising all members of both sets. The intersection is the set comprising those members which are in both of the sets. So it's like the AND function of propositional logic. And the complementation can only be understood in the context of a universal set, which you're using in a particular problem. And it's just all members of that universal set which are not in the set being complemented. We can also define sets by properties that their members share. So, for example, if we've got this set n of whole numbers between 1 and 100, then we can define a subset of n by defining, for example, E to be the set of all those members of n, such that when we divide by 2, that number is also a member of n, and that will be the set of even numbers between 1 and 100. So the way to read this is E is the set of those n belonging to big N, such that, read the colon as such that, n over 2 is also a member of n. We then looked at the idea of the universal set, which you always have to involve in any particular problem, and the empty set, which contains no members. And then a bit more notation, this union, if you like, on its side means subset, and that simply means that every member of the set E is also a member of the set N. It doesn't preclude the possibility that E and N are the same set, are equal. It could be that E is a smaller set than N, or it could be that they're equal. And then we looked at this very simple notion of diagrammatic representation of sets, Venn diagrams, and in particular looked at Venn diagrams with 3 sets represented by 3 circles intersecting in various ways. I also went on to look at the idea of cardinal numbers. So with a finite set, this is a very trivial concept. It's simply the number of members that the finite set contains. But when you get onto infinite sets, it's somewhat less trivial, and you can regard 2 infinite sets as having the same cardinal number if it is possible to set up a pairing between members of the 2 sets, which leaves no member of either sets unpaired, and then the 2 sets have the same cardinal number. We also looked at the idea of power sets. Well, the power set of a set is just the set of the set of all possible subsets of the set, including the empty set and the whole set itself. And we looked at the idea of partitions, which is a collection of sets which between them make up the whole set being partitions and which do not intersect with each other. And this turns out to be useful in probability later in the module. I then went on to look at particular sets of numbers. The simplest infinite set of numbers is the set of natural numbers, starting at 1, going up 2, 3, 4 ad infinitum. Not meaning that there is an infinite element, but meaning that you just never exhaust the new members you can write down. It should be noted some books and some mathematicians say you should include 0, the number 0 in the natural numbers. I've chosen not to in this module. I guess it's a matter of choice in some sense. Then the next set is the set of integers, which includes the number 0 and all negative whole numbers. And although that is clearly a superset of n, in the sense that every member of the natural numbers, every natural number is also an integer, but there are integers which are not natural numbers, it nevertheless turns out that these two sets have the same cardinal number, because you are able to set up a one-to-one pairing between the members, which leaves no members of either set unpaired. Even more surprisingly is that the set of rational numbers Q has the same cardinal number as the set of natural numbers and the set of integers. Of course, the set of rational numbers are just ratios of whole numbers, m over n, where m is a whole number, positive, negative, or 0, and where the denominator number, little n, is a natural number. And then finally, without going much into the nature of it as a set, I mentioned the idea of so-called real numbers, which includes the irrational numbers such as the square root of 2 and pi and so on. We then look briefly at Cartesian products of sets. So the product of the two sets, capital A and capital B, is simply the set of ordered pairs of members from those two sets, where the member from the set A comes before the member from set B. Again, there's a bit more notation here. Ordered pairs are delineated by round brackets as opposed to the curly brackets of sets. So all this right-hand side here is saying is that the Cartesian product big A times big B is the set of ordered pairs AB, where A comes from big A and little b comes from big B. Of course, this is particularly useful in planar geometry, where you can represent points in the plane by their Cartesian coordinates, which is simply an ordered pair of real numbers, x, y, x being the horizontal components of the point and y being the vertical component of the point. And then we finish by looking at the overture to probability, the next subject in the module, and simply because set theory plays a vital role in that. So we consider in probability a sample space to be a set containing all possible outcomes of some experiment that we're going to perform. And then events are simply subsets of that sample space. So for example, if we're just rolling a die, then the outcomes are the numbers 1 to 6. And we might have an event such as the score is even, which would be a subset of the sample space, namely the subset containing the numbers 2, 4, and 6. So moving on to the fourth subject, that was probability. And of course, this makes use of the combinatorics and the set part of the course. So, as I said at the end of the section on sets, probability involves the idea of a random experiment which can have a number of different possible outcomes. The sample space is then simply a set. It's the set containing every conceivable possible outcome of the experiment. And then an event is some subset of that sample space. So set theory comes in at that level. Now we can think of carrying out an experiment a large number of times. So if, for example, we were rolling a single die and we wanted to know the probability of the score being even, then we could roll the die 100 times, count how many times we get an even result, 2, 4, or 6, and then divide that number by 100, and that would give the so-called relative frequency of an even score in 100 throws of the die. Of course, we would expect that as n, the number of repetitions of the experiment increases, that will get closer and closer and closer to being some fixed number. If the die is fair, it should get close to being 1/2, because 1/2 the scores are even and 1/2 of the scores are odd. So that gives us one way of defining a so-called probability of an event. A probability of event is simply a number between 0 and 1. 0 means that the event can't or is very unlikely to occur. 1 means that it's certain to occur. So we can define probabilities either by taking an experiment, possibly not knowing the nature of the experiment and how it works. It might be a black box that we press a button on and it produces a random number, and then we have to count the number of outcomes in a large number of repetitions of the experiment to come up with the relative frequency and hope that settles towards a steady value and call that the probability. There is another technique, which is if we know how the experiment works, which we certainly do in the case of rolling a single die, if we know that the block of wood that the die is made out of has got uniform density, then there's no reason to suppose that any one score is more or less likely to occur than the other. And from that symmetry idea, we could just divide up the total probability of 1 between the 6 possible outcomes, scores 1, 2, 3, 4, 5, 6, to make them probability 1/6 each. And of course, under that assignment, we will once again get probability of 1/2 of an even score, because that would be the sum of 2, 4, and 6 probabilities. This idea of adding probabilities relies on events being mutually exclusive. Two mutually exclusive events are simply events which have no outcomes in common. So thinking of them as sets of outcomes, their intersection is empty, equal to the empty set. If that's true, then the probability that the probability that one or the other occurs, the probability their union occurs, is the sum of their individual probabilities of occurring. So that's the additive law of probabilities. You can only do that if the events are mutually exclusive. Taking that idea forward, there's this very useful idea of a partition, where you can partition any event into a set of sub-events, which together make up the whole of the original event, and which are mutually exclusive. And in that case, the probability of the original event is the sum of the probabilities of the sub-events. Going on to look at particular examples, when we want to calculate probabilities, one of the situations we can be in is one in which all outcomes have equal probabilities. And that's true, for example, of rolling a single die. All 6 outcomes have the same probability, 1/6. It's also true of throwing 2 dice, where there are 36 possibilities going from double 1 through double 6. If outcomes all have equal probabilities, then it's very easy to calculate probabilities of events. We simply count the number of outcomes of events in the event in question and divide that by the total number of outcomes in the sample space to come up with a probability. Note, however, that this is not possible unless the outcomes have equal probabilities. And we looked in particular in the problem sheets at the experiment of flipping a coin an arbitrary number of times until we first get heads. So first thing to note here is that there are infinite number of outcomes in the sample space, because there's no upper bound on how many times we may need to flip the coin before we get a head. And now, of course, the probabilities are not all equal. So the number of tosses would be 1 if we flip the coin once and get it first time, and that's got probability of 1/2. To get for the number of tosses before we get heads to be 2, we have to have tails on the first flip, which is probability 1/2, heads on the second flip, which is again probability 1/2. 1/2 by 1/2 is 1/4, and so on. So the probabilities of the individual outcomes go down as a half, a quarter, an eighth, a 16th, and so on. And if we want to calculate the probabilities of other events, we've just got to add up the probabilities of all the outcomes which are contained in that event. So going on to the idea of a multiplication law for probability, we need, in order to do that, the notion of independent events. So two events A and B are independent if and only if the probability that they both occur, the probability of their intersection in the set theoretic sense, is the product of them individually occurring. This is, of course, not generally true of arbitrary events A and B. We can then go on to the notion of independent partitions, which are two sets of collections of events, and then partitions are only independent if every event in one partition, in partition 1, is independent of every event in partition 2. More generally, when events are not independent, it's useful to calculate so-called conditional probabilities. I gave a formula for this. So the probability of A conditional on B is simply the probability that A and B both occur divided by the probability of B occurring. Of course, if A and B are independent, then the numerator here is just the product of PA by PB, and so PB's cancel, and we just end up with PA. We get the conditional probability is the same as the straight probability PA. So this measures the degree to which the events are not independent. I then finish off by looking at the idea of a random variable. So this is just a numerical valued quantity whose value depends on the outcome of the experiment. And we looked at the definition of the so-called mean, the average value of the random variable, and variance, which is the measure of the spread of values around the mean, involving the expected value, the average value of the square of the random variable. And in particular, I looked at the binomial distribution, which is the distribution, for example, of the number of heads you get if you flip a fair coin 8 times. You could get no heads, 1 head, all the way through to 8 possible heads. So the random variable takes values from the set 0 to 8 inclusive, and the binomial distribution calculates the probabilities of those events. So moving on to the final subject, we looked at matrices. So a matrix is just a rectangular array of numbers. And we looked at the very easy notion of matrix addition and multiplication of a matrix by a scalar, a single number. So for example, if I've got a 2 by 3 matrix, that's 3 rows, 3 columns, containing entries 1, 2, 3, 4, 5, 6, and I add that to twice the matrix, again in a 2 by 3 matrix containing the entries 2, 3, 4, minus 5, minus 6, minus 7, then the result is a 2 by 3 matrix, where in order to find this term in the first row, first column of the answer, I just add the terms of the first row and first column of the 2 matrices I'm adding. And of course this 2 sitting outside the matrix multiplies each of these numbers. So that this number 5 here is 1 plus 2 times 2. The 8 is 2 plus 2 times 3, and so on. Just like ordinary, just like there's matrices admitted in algebra, you can have unknown matrices and manipulate equations to calculate what the matrix or unknown matrix actually is numerically. And of course that means using normal rules of algebra, like doing the same thing to both sides of an equation to retain inequality. Somewhat less trivial is the notion of matrix multiplication. And the starting point for matrix multiplication is to look at the product of a row vector and a column vector. In order for this to make sense, the number of entries in the row vector must equal the number of entries in the column vector. So in this example here, both vectors got 3 entries. And then the product of the row vector 2, 3, 4 by column vector 1, minus 1, 2 is just simply the first entry of the row vector multiplied by the first entry of the column vector, 2 times 3, 2 to 1, sorry, plus the second entry of the row vector by the second entry of the column vector, 3 times minus 1, plus the third element of the row vector by the third element of the column vector, 4 by 2. So adding those numbers together, we get 7. So multiplying a row vector by a column vector can only be done if they have the same number of members. And if they do, then the result is just a scalar, a simple number. So this is the basis for multiplying more complex matrices. So if we've got 2 matrices A and B, A has L rows and M columns, it's a so-called L times M matrix, and B has M rows and N columns, it's a so-called M times N matrix. Then the key feature here is that the number of columns of A, M, has to match the number of rows of B, again also M. If that's the case, then the product AB is well defined, otherwise it makes no sense. And the product will have the same number of rows of the first matrix, namely L, and it will have the same number of columns of the second matrix, namely N. And then you can find the numbers in the product, which is an LIN matrix, by going through the numbers in the matrix one at a time. If you're looking at the number in ith row and jth column of the product, you find it by multiplying the ith row of the first matrix A by the jth column of the second matrix B, as indicated on the previous slide. If they're both well defined, then AB, the product AB, need not equal BA. For example, if L is equal to N, then the product BA is well defined, but it doesn't necessarily even have the same dimensions as AB, so certainly wouldn't necessarily be equal to BA. So this is one of the features of matrices that distinguish them from ordinary numbers. Multiplication is not commutative. AB is not necessarily equal to AB. Also arising in the notion of products of matrices is the idea of an identity matrix. So this is like the number 1 of ordinary algebra. So if you take some number, say 3, and multiply it by the number 1, you still get the number 3. It doesn't change the result. It's 1 times 3 is 3. So the equivalent in matrices is our so-called identity matrices. They're always square matrices. That's to say they've got the same number of rows as they have columns, and they contain 1s in the leading diagonal, but 0s everywhere else in the matrix. So the 2 by 2 identity matrix is 1, 0, 0, 1, and the 3 by 3 identity matrix is 0, 0, 0, 1, 0, 0, 0, 1. And they behave the number 1 in ordinary algebra. So for example, if I've got some arbitrary matrix A having M rows and N columns, then product identity matrix of order M times A makes sense, as does the product of A multiplied after by the identity matrix of order N, and they both products work out to be equal to A. And of course, you can check that with some examples. And then we get the idea that multiplying the coordinates of points in the plane, as represented by the ordered pair of x and y coordinates, can be viewed as implementing transformations of the plane. So, for example, multiplying by a diagonal matrix just scales the x and y components, possibly by different scaling factors. We also look at rotation matrices. These are of the form cos theta sine theta and sine theta cos theta in the 2 by 2 setting, and they have the effect of rotating a point about the origin of the plane by an angle theta. We went on and looked at the idea of inversion of 2 by 2 matrices, which in the context of transformations of the plane, will undo any transformations that are affected by that are implemented by multiplying by the original matrix. The first step in inverting a matrix is to calculate its so-called determinant, and this is normally indicated by straight lines around the matrix. And determine the 2 by 2 matrix, general 2 by 2 matrix containing components little a, b, little c, little d, is just simply a times d minus b times c, the product of numbers on the leading diagonal minus the product on the diagonal. And that, if we look at the determinant of a matrix we've used to transform the plane, that has an interpretation of scaling any enclosed areas by shapes. So, for example, we have a circle in the plane and we transform points by multiplying by a matrix, then the area contained in the circle will be scaled by the determinant of the matrix. The main application of determinants is as part of the matrix inversion process. So if we've got a general 2 by 2 matrix A, B, C, D, then its inverse, its multiplicative inverse, is the scalar 1 divided by the determinant of the matrix multiplied by this matrix here, which we get by interchanging the numbers on the leading diagonal. D and A get swapped, and by negating the terms off the diagonal, but not swapping. Of course, this only makes sense if the determinant of A is non-zero. Cannot divide 0, it makes no sense. So only matrices which have non-zero determinants can invert. And what the occasion of the matrix inversion is solving a system of linear equations. So, for example, if we have two unknowns x and y, and we have two linear equations relating them, then we can express that as a single matrix equation, and then invert a matrix in that to get the solution of the two lines that both satisfy. A graphical interpretation is that each of the linear equations is the equation of a straight line, and the point where they're both satisfied is the point at which the lines intersect. That's a very hasty dash through the subject. Of course, you've got all the other tools available to you. The notes are on Moodle. Problem sheets and answer problem sheets are there. Please feel free to ask questions through the frequently asked questions format.